Uncertainty principle, read out whatever he has written. We have already discussed some experimental aspect. Okay, uncertainty exists between x and px, sigma y. This is standard deviation. Standard deviation is the measurement of x, standard deviation in the measurement of px. Okay, now look at here. While defining the standard deviation, you should again go for all quantum mechanical idea, identically prepared system, measurement, result, standard deviation, like that. Is that okay? So identically prepared system, measurement of momentum, like that. Is that okay? So greater or equal to h bar by 2 sigma y, sigma py greater or equal to h bar by 2. We can define a state. Okay, we can define a state where sigma x into sigma px is equal to 0. Sorry, sigma x into sigma py is equal to 0. There will be no uncertainty between them. That's what we say. We can do well-defined x position state, well-defined y momentum state. Okay, let me try to give some example for this one. So, but uncertainty exists in that what you call respective canonically conjugate variable. Is that okay? We can't define a state which has well-defined both canonically conjugate variable. Can I say like this? Yeah, sigma z, sigma pz greater or equal to h bar by 2. So Griffiths gave a good example to understand this uncertainty. Just read out that one, or a rope example. Okay, well-defined momentum, ill-defined position, well-defined position, ill-defined what you call momentum. Okay, read out that one carefully. Okay, now I'll go to next chapter because I again while giving the assignment, that will be very easy for me. Is that okay? I can give next topic together as a assignment. Okay. Time independent Schrodinger equation. I'll write it as TISE, time independent Schrodinger equation. Is that okay? Yeah. Now look at here. So this is a Schrodinger equation. IH bar dou. Let me write psi like this. Okay. So that again we use two psi here. This capital psi means psi of x comma t. Okay. Later we use one small psi of x alone. Single variable function, two variable function, time as well as space. Okay, single variable function like that. Okay, that's why I'll use other symbol for psi, this kind of psi. Okay, so dou psi by dou t is equal to minus h bar square by 2m dou square by dou x square psi plus v of x comma t. Psi means psi of x comma t. Psi means function of x and t. Okay, partial differential equation. We need to solve that partial differential equation. Again, I will restrict myself to the situation where potential is independent of time. Okay, potential, time dependent potential we shall take in quantum dynamics. Okay, if potential changes with respect to time, we call that one as dynamic situation, a kind of dynamic situation. Okay, so again, so potential, I'll assume again, so next 3 to 4 to 5 chapter, again we are going to again restrict ourselves that v is equal to v of x alone, independent of time. Okay. Is that okay? Independent of time. In that situation, let me just rewrite here. Okay, let me save some time. I'll write like this, v of x. I'm restricting myself to next 2 to 3 chapter. We are restricting ourselves to the situation where our potential is depending only on the position, conservative field, okay, and it is independent of t. Okay, v is so then if potential is time dependent, then first we go for perturbation theory actually, time dependent perturbation theory. So if potential is time dependent means your Hamiltonian is time dependent, am I right? T cap plus v cap. If this is time dependent means your Hamiltonian is time dependent. Okay, time dependent Hamiltonian, again that is discussed in quantum dynamics or again in the perturbation theory also, time dependent perturbation theory. We shall deal with that one later. Okay, now so in this kind of situation, this is a partial differential equation, isn't it? You can see there's a partial differential equation. This partial differential equation can be converted into two total differential equation. I hope you know something about partial and total differential equation. Okay, so total differential equation contains d by dx like that, okay, not dou. Dou is for, again, if it has a two variable function, definitely partial derivative will come, okay. We can convert this partial differential equation into total differential equation by separation of variable. Look at here. Now what we do is, there are many solutions for this one, partial differential equation. Among those solutions, we are going to choose this kind of solution because it has lot of properties, okay. Among all possible solutions, again, we are going to restrict ourselves to this solution. We call it a separable solution. That means this combined function, two variable function, can be written as product of single variable function. We call that as variable separable. Not variable separable differential equation type. Separating variable. Separation of variable to convert partial differential equation to total differential equation. So if you put this one, it will be quickly converted into total differential equation. Why? In any physics application, we do this one. We do separation of variable and then we convert that one into total differential equation. We solve total differential equation actually. Is that okay? So that's why I think they developed some other theory for time dependent potential. If potential is time dependent, you can't separate variable. You will see that one later. Okay, if potential is time independent only, you can separate the variable, you can convert that into two total differential equation. Okay, yeah, any question? Yeah.
So
now,
is potential a complex?
No, potential is complex, is very rare situation. He gave one problem in first chapter. Can you look into that one? Complex potential.
Yes, sir. But if we see that Schrodinger derivation, that left hand side is complex.
But this potential is classical physics conservative field potential only. That's always real, isn't it? Yeah. But x should be replaced by x cap. But x cap is x itself. That's why we write v of x. We don't write v cap actually here, isn't it? Because x cap is x itself.
How potential will
complex. No, I mean, there are some situations, there are some modeling he gave. Yesterday, I just saw that problem outside first chapter. Just look into that. But in the case that we are applying, we don't take any what you call complex potential. Okay, time independent potential. So again, out of all possible solutions, again we pick this solution. Okay, and this solution have got lot of what you call property. What we can do is we can linearly combine this kind of solution to make non-separable. This is separable solution, am I right? You can take space part one side, you can take time part one side. What you can do, you can linearly combine different of this kind of solution, and you can form most general solution, which is non-separable. You will see that one later. Is that okay? You can write like this: psi 1 of x, phi 1 of t, plus psi 2 of x, phi 2 of t, like that. So you can linearly combine C1, C2 like that. So now this solution, look at here, this cannot be separated. This kind of solution, you can't write x alone, t alone as a multiplication. Yes. So that's why this has lot of property, lot of special property. That's why even though among all possible solutions, we are picking up this one. So that's not a bad deal. Is that okay? Yeah. Now substitute back into equation. What will happen is I h bar dou by dou t of psi of x into phi of t, that's equal to minus h bar square by 2m dou square psi of x into phi of t by dou x square plus v of x into psi of x into phi of t. These are given in Griffiths, that's why I am doing quickly. I can take phi of t outside. Here I can, here I can take psi of x outside, partial derivative with respect to time here, isn't it? Here I can take pi of t outside. Now what I do is I'll take that one outside. I'll divide whole equation by psi of x into pi of t. After taking that one, dividing whole equation by psi of x into pi of t. Is that okay? Then what will happen is I h bar psi of x came outside, 1 by pi of t will remain. Just check that out, okay? Now this becomes total derivative d, because now you are taking derivative of single variable function, d phi of t by dt, that's equal to minus h bar square by 2m into 1 by psi of x after division. Okay, after division. I'm writing one step directly. So check that out later. Psi of x plus v of x. So take this psi of x outside and divide by psi of x into pi of t. Okay, take this pi of t outside, divide by this one. So again, this is nothing, you just divide by psi of x into pi of t. You will end up with this one. Observe this one very carefully. This part depends on time alone, isn't it? This part depends on space alone, isn't it? Space means x. Is that okay? This part depends on time only. This part depends on x only. Now look at here. X and t are independent variables. Independent means, can you imagine? Y and x are independent. Y axis here, x axis here, isn't it?
So they can't linearly combine them.
Wait. Not linear combine. X axis.
Yes, sir.
That means you can vary x without varying y. You can go to parallel to x axis. You can vary y without varying x. Is that okay? That's the meaning of independent variable. Is that okay? Suppose if these axes are like this, if you move like this, both I think here also you can vary only one, isn't it? You just move perpendicular to one axis. You can do that. Okay? Yes. So now look at here. We call them as independent variables. Similarly, this x as well as t are independent variable. You can vary t alone without varying x at one position. You are observing what is psi of x, psi of x comma t. Okay, so like that. Again, you can take the wave function at one instant of time. You can observe what happens with respect to x. You can take one position in space. You can talk about what happens with respect to different time. Isn't it? They are independent variable. You can vary time without varying x. You can vary x without varying time. Can I say like this? Now, in that case, if you vary time, okay, without varying x, okay, if you vary time without varying x, only this part will be varied. This part will not be varied, isn't it? If this part varies, this equality is gone. Okay, look at here. If t is varying, x is equal to constant. Okay, this part will not vary, but this part will vary. That means if it varies, then that equal again. If this is constant, if this varies, then this equality will become inequality. That equality will not be valid if it varies, isn't it? So similarly, if x is varying and t is equal to constant, so then what will happen? If t equal to constant, this part is constant. If x varies, if this part varies, then equality will become inequality. Equality will not be whole, isn't it? If x is varying, if this whole part is changing as x varying, then this will vary from the initial value, but this will not vary. So that's why this can happen only when both of them are equal to some constant.
Equal constant.
Yeah. This should be also constant, this should be also constant, then only this kind of relation is valid. Write down again, think over it. Yes. So now, if x is varying, t equal to constant. If t equal to constant is this part is constant, okay, this will not vary if you vary x, isn't it? Now, so this is constant. So if suppose this varies, then equality will not be followed. If you take different x value, if suppose this is a variable. So that's why to follow this equality for all time, for all space, both of them should be constant. Is that okay? I'll come into I'll come into what is this constant later. Okay, so I'll call that constant as E. Later I'll argue that is energy. I'll call you this constant as E, separation constant. We call this one as, this is not E cap. Okay, this is not E cap, this is E. We call that one as separation constant. Later I'll argue that it is energy. Now you got two differential equation. You got two differential equation. One differential equation is IH bar. So let me take this phi of t there, okay? D phi of t by dt is equal to E into phi of t, or d phi of t, let me rewrite this one, d phi of t by dt, that's equal to minus IE by h bar into pi of t. Now look at here, this differential equation can be solved. Again, this differential equation contains potential, but this doesn't contain potential. Can I quickly solve this one? Variable separable. Again, we shall discuss this one in the next session, okay? D of phi of t divided by pi of t is equal to, speak out, minus IE dt by h bar, okay? If you solve this one, this will be log of pi of t, that's equal to minus IE t by h bar plus some c, plus some constant of integration. I write that one as log of some constant, some other constant, a. Is that okay? So write down this one and again think over it, okay, this part. So now this will be, look at here, log of pi of t divided by a is equal to minus I e t by h bar, okay? So that pi of t is equal to a e power minus I e t by h bar. I will not take a here, okay, because anyway your total wave function is a product of psi of x into phi of t, isn't it? Later we need to normalize the whole wave function. That's why I'll not take a here. I'll take the a along with the psi of x. Anyway, this is constant, am I right? Now at least at this stage you should be confident to multiply or divide a wave function by any factor. It will not change any physical situation, isn't it? That's why I'll take this constant along with this one. Anyway, later we need to normalize. Later we need to find a multiplicative constant which normalizes that one. That's why I'm not worried about this one. Is that okay? I'll just rub out this one. If any constant is there, let me find along with these two. This also may contain some multiplicative constant. This also may contain some multiplicative constant. Let me multiply those multiplicative constant together and I'll find that one during normalization. Is that okay? That's why I'm not worried about that one. So this is one part of the solution. Pi of t, we got it. Is that okay? Now what is other part? Look at here. IH bar, sorry, not IH bar. What is other part? Minus h bar square by 2m d square psi by psi of x, okay, by dx square. Earlier whatever psi I was writing in the last chapter, it was psi of x comma t, most general wave function, okay? Usually that's why I was trying to write big psi in the last chapter, okay, because here comes 2 psi. That's why I made the what you call fixing, okay? I call capital psi as like this, I call small psi like this. Is that okay? That's the best idea. So plus v of x into psi of x is equal to separation constant into psi of x. We call this one as time independent Schrodinger equation. And next our idea is to solve this one in most of the cases. To solve time independent Schrodinger equation. This is for 1 dimension, you can generalize that one for 3 dimension. Is that okay? That time part remains, okay? Even if you generalize this one for 3 dimension, time part remains. Suppose if you are talking about psi of r comma t, okay? Write it as psi of r pi of t. Spatial part one side, time part other side, and do the same step. So then del square will come here, okay? Just like I have written. Again, first we shall discuss 1 dimension, later we shall go for 3 dimension. In case of 3 dimension, del square will come here. That's again 3-dimensional, partial differential equation. While converting that one into total differential equation, you come out with the same idea, separation of variable. There all are spatial variable, x variable, y variable, z variable. Here 1-dimensional problem, x variable and time variable I separated and I found time independent Schrodinger equation. Our effort is to solve this one in the next place, okay? So along with this one, look at here. Along with this one, if you define pi of t, what is pi of t? E power minus I e t by h bar, your total solution is done. If you find psi of x from this one, pi of t is already, it is same for all. What do you mean by different problem? Different problem is different potential. Is that okay? So that's why this part will not change. This part was, again, that part of differential equation doesn't contain potential. Isn't it? It contains some time derivative, energy, this energy and all, isn't it? So that's why, so look at here, this is equal to psi of x into e power minus I e t by h bar. Separable solution. We call this one a separable solution. Wait a second, without, before getting into that one, before getting into next part, okay, we shall rewrite this equation, okay. You should read little bit about eigenvalue and eigenfunction, okay, because that is, that we are going to study in the third chapter actually, okay, because lot of mathematics okay, we need lot of mathematics once here, okay, to discuss many quantum mechanics, but I'll discuss one by one parallelly, okay, just like differential equation and all, okay. Now this whole thing, look at here, we are going to rewrite, what is this one? This is p cap square actually, isn't it? This is p cap square. So now look at here, so this can be seen like the p cap square by 2m, so into psi of x, plus v cap, vx, a cap is v cap is vx itself, because x cap is x itself, isn't it? So into psi of x is equal to e into psi of x. Is that okay? E into psi of x. Now look at here. Now this whole thing I am going to write it as p cap square by 2m, actually px here, okay, plus v cap operating on psi of x is equal to e into psi of x. This one I am going to write it as Hamiltonian operating on psi of x is equal to e into psi of x, where e is a separation constant. I still have to argue how that is energy. Is that okay? We call this one as eigenvalue equation. Eigenvalue equation. Operator operating on a function, constant times the same function.
But E is a constant, right?
E is a constant, yeah, that's what I'm saying. Operator operating on function, some constant into the same function. We call it as eigenvalue. After operating operator, that functionality is not changing. Function is multiplied by a scalar on constant. We call that one as eigenvalue equation. Let me explain that one a little more.
Constant becomes eigenvalue. Why?
This constant, we call that one as eigenvalue. That's the name of that one. It's becoming eigenvalue, okay? Eigenvalue equation. Eigenvalue equation. Now h cap into psi x is equal to e into psi x. E, again, this is called as eigenvalue operator, okay? Eigenvalue operator. This is called as eigenfunction. This is called as eigenvalue. Can you write this down? Eigenvalue operator, eigenfunction, eigenvalue, eigenfunction. That's why sometimes I call this one as psi of x as eigenstate of Hamiltonian. Eigenstate of energy, because Hamiltonian represents energy here. Energy is represented by Hamiltonian operator here. Is that okay? Yeah. After this observation, I will go back and I will see this time dependent Schrodinger equation in a quite different way. Dou by dou t of capital psi is equal to minus h bar square by 2 whatever you have written. Am I right? Can you write it as h cap into capital psi? I'll see that equation in a quite different manner. Now, what is time dependent Schrodinger equation? Time dependent Schrodinger equation is operating h cap and on psi, that is equal to operating I h bar dou by dou t on psi. Isn't it? see that equation in a different manner now in terms of operator, because we'll get into Dirac idea later, operator thing. Is that okay? Now look at here. Operating Hamiltonian. So I hope you know this one. This is minus h bar square by 2m dou square by dou x square psi plus v psi, isn't it? So this one, what I do is I h bar dou by dou t of capital psi. Okay, so that is equal to minus h bar, again this is equal to h cap into capital psi. Now what we do here is h cap is a operator corresponds to energy, am I right? Operator which is a representation of energy. That's why this should be also kind of energy operator, I h bar dou by dou t. We call that operator as E cap. Not much use of this operator, okay? Not much use of this operator, but this is called as energy operator. E cap psi is equal to h cap psi. This E cap is not this E. This is scalar. There is no cap here. There is a constant. This is E cap. E cap, we are going to say, we are going to write this E cap is equal to I h bar dou by dou t. You know already what is h cap. Now this is the way of seeing time dependent Schrodinger equation. We call this one also as energy operator. Not much use of this one, okay? Later we shall see E cap plays the similar role for as a h cap, okay? Again, in place of h cap we can place E cap while solving any problem and all. But we don't do that one. We use this one only, okay, while solving problem. Okay, not much use of this one, but this is called as what you call energy operator. Okay.
But here there is no eigenvalue equation, right?
No, here it is not E. This is E. That's what I'm saying. Don't say this is same as this one. This is an operator. This is a scalar, constant.
Okay, there is different equation.
This is time independent equation. This is all we got. This is time. Yes, sorry. This is time dependent equation. Time dependent Schrodinger equation. Psi x comma t. Can I write like this? Actually, the evolution, again, you should see some modern quantum mechanics. Then I think this kind of problem would not come. Anyway, look at here. This E cap is different. I'm talking about time dependent Schrodinger. The way of seeing time dependent Schrodinger equation is like this. The way of seeing time independent Schrodinger equation is like this. Now, time independent Schrodinger equation is an eigenvalue equation. Time dependent Schrodinger equation, we'll talk about operating this one is similar to operating this one. If you operate on this one, whatever you get, that is same as if you operate on this one. Like that. This is a kind of operator into function, operator into function. This is different. Operator into function, constant into function. Find the difference. Find the difference. Over?
Sir, E cap and H cap both are almost same, sir.
They play the similar role. We shall see in some problem later. In place of H cap, you can put E cap, you will get the answer. You will get the answer. We shall see. But for time independent function, you can't use E cap. You will get 0 only when you operate that one. Okay, that's the difference. Yeah. Now, okay, I hope you got again these things. How to see this one? Okay, how to see this one? This is also another operator. Okay, this is also another operator. Again, this is Hamiltonian operator. This is the way of seeing this one is a kind of eigenvalue equation. That's why many times we say this psi of x as eigenstate, or sometimes we say that this psi of x as an energy eigenstate. Because of this equation is called as eigenvalue equation. So this is called as eigenfunction or eigenstate. Eigenfunction, eigenstate, both are same. Is that okay? Eigenfunction, eigenstate, same name. We are going to use that one. Psi as energy eigenstate. We say like that. Is that okay?
So I hope it will not confuse E and E cap.
That's why I have introduced here.
Yes, sir.
Once you learn these two at the same time, I hope now you got the distinction. This is not cap. This is cap. This is we are talking about. I'm talking about time dependent Schrodinger equation here. This is time independent Schrodinger equation here. This is operator function, time dependent function. Okay, x comma t. This is operator psi of x only, constant into psi of x. Time independent Schrodinger equation. Way of seeing the equation. Okay, that's why.
So, sir,
Yeah. Yes.
sir, here time dependent Schrodinger equation. How can we physically interpret this one?
Time dependent or independent?
Time dependent, sir. Time dependent.
No, that's what I'm trying to say. This is physically meaning is operation of this one on this state. Okay, this psi of x comma t. You get something that is equal to the thing that you operate e cap on the same thing. It is to say that these two operators are equivalent. Their action on the function are equivalent. That okay? E cap, H cap. Can you see this one? X comma t, that's equal to H cap psi of x is equal to E into psi of x. Scalar operators, time dependent function, time independent function. Is that okay? Is that okay? Find the difference. Find the difference. They are operators. Okay. Now look at here. I'll just put a hold on this one. Maybe in the third chapter we will discuss more about this one. But sometimes I call this one as eigenstate, energy eigenstate, or I call this whole thing as energy eigenstate. Because of that one actually, because that is eigenvalue equation. Okay, eigenstate, the word that we use. Okay. Now we shall concentrate on this one. This is separable solution. Am I right? What is so special about separable solution? Okay. What are the properties of this separable solution? Shall I rub this out? Yes, tell me.
You said that psi x can be said as eigenstate. But how can psi as a function of x comma t both be called eigenstate?
No. Well, look at here. H cap operated on. So psi of x into e power minus I e t by h bar together. Okay. So that's also equal to E into psi of x into e power minus I e t by h bar. Look at it, just multiplying with this time factor. Equation is same.
This does not go to upper equation, sir, that comes from.
What I'm saying is, yeah, that's true. So this together also called as eigenstate, because if you multiply with this factor, Hamiltonian doesn't operate on time factor. Hamiltonian contains dou by dou x kind of operator.
Yes.
That's why even though you multiply, this eigenvalue equation is satisfied. Is that okay?
And sir, compare with the upper equation, sir, comes from the time.
Again, this one as well as this one is called as eigenstate. That's what I'm saying. It is not. This is not an eigenvalue equation at all. This is not eigenvalue equation at all. This is the most general solution. This may be like this, or this may be linear combination of this. You will see later. This is the most general solution, capital psi. So again, this may be like this, that may be like this, or that may be combination of different of this one. We shall see later. Is that okay? This is not generally called as eigenstate, but this is called as eigenstate. This is called as eigenstate of Hamiltonian, because if you plug in this factor, then also eigenvalue equation is satisfied. Am I right? Eigenvalue operator, some function, constant into the same function. That is satisfied. That's why this together also called as eigenstate, energy eigenstate.
Sir, your last one equation and middle equation for the same time.
Yeah, these two both are called this. That's what I'm saying. Psi of x is also called as eigenstate, energy eigenstate. This together is also called as energy eigenstate. That's what I'm saying. Okay. Suppose if you linearly combine, if you write your wave function, psi 1 of x into c1 psi 1 e power minus I e1 t by h bar. Okay. Plus psi 2, so e power minus I e2 T by H. If you linearly combine, you can't call it as eigenstate. Suppose if you operate Hamiltonian, just operate Hamiltonian and check this out. You will not get constant into same function. I'll come to that one in a moment, okay? I'll come to this one, linear combination state, okay? But this is called as eigenstate, energy eigenstate. This is called as energy eigenstate. Now look at here. Time independent Schrodinger equation. What is this one? H cap psi of x is equal to E into psi of x. Now, what is so special about, I better write this H cap operator like this, isn't it? Operator. Scalar. Operator. Time dependent Schrodinger equation. Can you recognize these colors? It doesn't look as good as it looks in our eyes actually. In the
Not much difference.
not much difference. No use, isn't it? Yeah. Now look at here. Psi of x, separable solution, okay, not linear combination. Linear combination, I'll come to this one. Again, we call this one as separable solution, okay? Separable solution. So that means psi of x comma t, if psi of x comma t is equal to psi of x into e power minus I e t by h bar. Okay, what is so special about this one? This can be combined, that's also solution. I am not talking about combination of this. When you solve this one, you got one energy. When you solve this one, you got one wave function. Am I right? When you solve this is a differential equation. Okay, so I am just talking about that one separable solution. What is so special about that one? First property, quickly. First property. They are stationary states. You can say particle is in this state, am I right? You can say particle is in energy eigenstate or eigenstate of Hamiltonian. You can say this one as eigenstate of Hamiltonian also. I told, isn't it? Eigenstate of Hamiltonian operator. Look at the words, eigenstate of Hamiltonian. They are stationary states. What do you mean by stationary states? Stationary, why the word stationary came here? Stationary is for static particle. Particle cannot be at rest in quantum mechanics. Uncertainty will be violated. Stationary doesn't mean particle is at rest, okay? Stationary means, look at here. Whatever the thing you do, expectation value, probability, what you take psi star into psi. What is mod psi x comma t whole square in this case? I'm just discussing this one, okay? This part is 1. Mod psi of x the whole square. Okay, expectation x independent of time is equal to, don't take, now we have two different things, okay, this is different, this is different. Suppose if you take expectation p, you can ask what happens for expectation p. Look at here, psi x comma t star p cap psi x comma t dx, psi star into psi. P cap operate only on this part. P cap operate only on this part. This part is remained. This is e power plus I t by h bar, e power minus I t h by h bar. So that's why this is equal to, look at here, psi star of x p cap psi of x dx. Any expectation value independent of time. Can I write? Time independent. So time independent. Actually, you can go for Unfest theorem. It is 0 itself. You can check that out. It is 0 in case of stationary state actually.
So what do you mean?
Even, yeah.
So for stationary states means it's not.
So wait a second. Any operator expectation is independent of time. Time independent. Time, any expectation values are independent of time. Probability density is independent of time. That's why the word stationary came.
Because of the here probability is independent of time. That's why all the expectation value are just
Huh.
independent of time.
You can say like that because everything started with probability explanation. Now one more thing, suppose you calculated expectation x using this one, am I right? Look at here, using time dependent state. You haven't taken t equal to some value, you have taken time dependent part only, but still it is independent of time. Now in this case you can apply your Unfest theorem. Again, I'll solve one problem, remind me. First chapter, I think last problem I mentioned, okay? When you can apply Unfest theorem, when you should not apply Unfest theorem. Suppose if you take t equal to 2 seconds, okay, in this one, then definitely it will not contain that time variable, isn't it? Are you getting it? In the most general case, suppose if you take t equal to 0, then if you find expectation x, then for expectation p, don't use that one because you have taken one of the time. If you keep time as variable, then only you can take derivative and you can use Unfest theorem, okay? Last chapter, last problem, first chapter, whatever I mentioned in the assignment, okay? He mentioned very strictly.
Sir, please once you repeat this statement, sir, please.
Now what I am saying is, suppose you have taken psi of x comma 2 seconds and using that one you found expectation x. Then don't apply Unfest theorem because you haven't let a time variable. How you can write dx by dt now? You can't write. Are you getting the point? That will be meaningless. Or so 0 second here. Is that okay? So that's very nicely given in the last problem of first, not last but one or something. Okay, in the first chapter I mentioned in the home. Yes.
So for using RFP's theorem, time part should be 0, t equals to 0.
I'm saying if time part, if you put 0, you should not use Unfest theorem.
Okay.
Did I said you should use? No. When look at here, Unfest theorem means expectation p is equal to m into d expectation x by dt, isn't it? Expectation x, if you write like this, x you have written, in psi you have taken x comma 0 second. How can you take time derivative of this one after putting one particular value of time, isn't it? You can't use this one in this situation. But in here, I have taken time as variable only, but it happened to be independent of time. I have taken time dependent wave function only. Okay, that's why what will happen in case of stationary state is expectation p is always 0. Look at here, according to Unfest theorem. Even if you take time dependent, time as variable in the everything, you will get 0, always 0. Expectation p is 0 in stationary state. I mean, I have written here. I just said this is time in 0 is also time independent. Is that okay? That's what I'm saying. I don't know what I told earlier. Remember, if you take some particular value of time, suppose t equal to 0 second, okay, don't use this kind of equation. That would be meaningless. That's mentioned in that problem. Okay, solve that problem. You will understand that. Okay, that problem is mentioned for that only. Suppose if psi x comma 0 is given, if suppose expectation p is asked, don't go for this one. This is only when you make the time variable, this equation. This equation only when the time is not set to some value, when time is kept as variable in the wave function. Yes, pick out.
Okay, sir. Okay.
Yeah, solve that problem. You will understand what I am saying here. Okay. Now look at here. Now, but I am not using any particular time. I'm leaving time as variable here, but still it happened to be independent of time. Okay. That's why this is 0. This is always 0. Any expectation value is independent of time. Probability density is independent of time. Expectation x is independent of time. Expectation p is independent of time. Let me say independent of time, but it is 0. Always. Is that okay? So that's why the word stationary came. Every expectation value is constant in time. He has written that one. Okay, read out that one. I'll give this one as reading assignment. Okay. First one, they are stationary state. They are also called as energy eigenstate. This wave function is our energy eigenfunction. Eigenstate are same. Is that okay? Energy eigenstate or eigenstate of Hamiltonian operator. Different name is there. Okay. Stationary state.
So this expectation of P is always 0.
Yeah, always 0. In case of stationary state, it is 0.
But in linear compression state,
It is not 0. You will see. That's why you need to solve more and more problem. Okay. In the linear combination, it need not be 0. You will see that one. But solve that problem. Okay. You can take this derivative only when you let this as a variable. Okay. By keeping this one as a constant, you can't take time derivative. That would be meaningless. I kept it as a variable, then I take time derivative, then I got 0. That's true. While applying Unfast theorem, be careful. That's what I am saying. Solve that problem, you will understand. Okay? Is that okay? Suppose,
we are taking the
look at here, sin x, okay? You take x equal to pi by 2. F of x equal to sin x, okay? You take x equal to pi by 2. Sin pi by 2, am I right? F of pi by 2. Can you take derivative of this one? Isn't it? You can take derivative of variable part, okay?
No, you are saying that time is variable, and we are not putting any value of that time. And
That's why you can make for this one, you can make d expectation x by dt. This is meaningful, and you can use Unfast theorem. And if I use Unfast theorem, yeah,
apply Unfast theorem, we have to see.
you have to take time dependent wave function. That's it. To apply Unfast theorem, you have to take time dependent wave function as time as variable. But what happened here is, even though it is time dependent, mod psi square is time independent. That's why that is 0. Derivative is 0.
Okay.
Is that okay? Yes. To apply Unfast theorem, take this Unfast theorem. Expectation P is equal to m into d expectation x by dt. While finding expectation x, take time dependent wave function. I have taken that one. It is 0. That's why it is true. That's why you can apply. And you can apply and you can say expectation P is 0 in case of stationary state. Is that okay? Second one. Now I am going to argue. The time. I'll give some exercise from class 12th today, okay? On basic math. Differential equation was there, isn't it? I mean, I think you have done some basic. Do variable separable in the evening, okay? So that I can save some time. Second one. They are states of definite energy. What do you mean by that one? We say everything is indeterministic in quantum mechanics, am I right? Position is indeterministic, momentum is indeterministic. But look at here, you got one deterministic part. They are states of definite energy. We shall see what is that energy. I haven't told E is energy. E is a separation constant still, okay? Wait a second, now I'll argue. So you have to read Griffiths carefully, you will get all of this side, okay? Now, Hamiltonian operator, what you write? P cap square by 2m plus V cap, am I right? P cap, or I'll write Vx itself, okay? Because Vx cap is Vx itself. This Hamiltonian operator represents energy, isn't it? Suppose if you need uncertainty in the position, what you did? You went for position operator, am I right? You found its expectation value, isn't it? Suppose if you need momentum uncertainty, what you did? So can I write like this? Expectation x cap square minus expectation x cap the whole square. What you did? Root of expectation px cap square minus expectation px cap the whole square. Am I right? Expectation px cap psi star px cap psi dx. Am I right? To find uncertainty in the measurement of momentum, you have used momentum operator. To find uncertainty in the measurement of position, you have used position operator. To find uncertainty in the measurement of energy, what should I use? Hamiltonian operator. Is that okay? Don't go for that energy operator. Both are equivalent, but don't go for that one. Okay, that's over. That part is over actually. We shall take that one in dynamics. Okay. Are you getting a point? Hamiltonian represents energy, or energy is represented by operator. We call it one Hamiltonian operator. Now, what I do? I have to go for what is this one? Speak out.
Expectation H square.
H cap square. Expectation H cap the whole square. Now look at it. I'll do in operator. He might have done using function and all. Okay. Shall I do it in operator way, or let me do it function later? We go for operator. Okay. This function we are taking stationary state. Okay. Should we name anything for this one? Because linear combination state we take similar. Okay. Or I'll name so linear combination like LS here. Okay. This is stationary state. Can I put yes here? Stationary state. Yeah. Now H cap operated on this one. Okay. This stationary state. We call this a state of definite energy. Am I right? That's equal to E into stationary state, isn't it? Even though you put this factor, you get the same thing, because actually it is H cap into psi of x is equal to E into psi of x. But even if you put that factor, you get the same answer, isn't it? Can I write like this? Is that okay? H cap psi of x into e power minus I e t by h bar, that's equal to E into psi of x into e power minus I e t by h bar. Okay. So how do you find expectation H cap quickly in this state? Okay. Psi star H cap psi dx. What is H cap into psi? I call this is a stationary state with separation constant T. Now, right now, okay? It's a stationary state with separation constant T. What is E? E is a separation constant, okay? H cap into psi. What I can write quickly? E into psi. That E can be taken outside. Scalar. E into psi star into psi. I'll take normalizable function, okay? Normalizable solution only. We restrict ourselves to normalizable function that only have physical meaning. Suppose I have normalized. What is this one? Because to find any expectation value, you should first normalize and then you have to move on, okay? Let me take this is normalized. To normalize that one, I need some specific example, okay? Suppose it is normalized. Let me assume like that. That's why this normalization constant that's equal to 1, okay? Look at here. What is average of measurement of energy? Speak out. What is average of measurement of energy?
Constant E, sir.
E. Separation constant T. Wait a second. Wait a second. Separation constant T. H cap square. Psi star H cap square psi dx. If you operate H cap twice, you will get E will come out twice. Can you see this one? Or do that one yourself again. So this will be E square into psi star. Do this one, okay? Operate this one once. E will come out. Again, one more H cap remain. Operate one more time. One more E come out, okay? Dx. That's equal to E square. Do you remember? Again, look at it. Average of square, measurement of square of energy. E square. Do you remember? Again, this happened somewhere. So that if I substitute here, what will happen? Root of E square minus E square is equal to 0. Do you remember when it happened? Energy X is here. Yes.
So there will be no distribution.
Yeah, there will be no distribution.
Sir, if no limit is given means minus infinity to plus infinity.
Minus infinity to plus infinity. minus infinity plus infinity. He too didn't take any limit. I mean, in case of particle in the box, it will become 0 to a like that, because outside wave function itself is 0. Okay. Better you mention the limit minus infinity to plus infinity, but you should know it is over all region. Okay. Then only it is true. But it should be understood. Okay. Whenever we do that one, unless we specify, you should integrate only this region. Okay. Now, whatever the measurement you do, you get, whatever the energy measurement you do, you get the same value, that is E. That's why that separation constant, I call it as energy. Why? It's an outcome of energy measurement. You feel I made you bakra? No. I mean, this is how it is defined, okay? Just check out, read Griffiths properly.
Technical.
It's a technical. Or sometimes sigma of E also, sigma of H cap actually, that's equal to 0. They are states of definite, before measuring also, you can say, yeah, you will get this energy only. If particle is in this state, you will get this energy only. They are states of definite energy. Is that clear? Every measurement of total energy will give the value E only if you take identically prepared system and if you do the measurement. Every identically prepared system with this state. Yeah.
Sir, if we increase the width of the wave, in that
The particle will be in linear combination state, not in stationary state. Okay. Width means he is talking about this width actually.
Distribution.
Then then we don't say that's stationary state. That's linear combination state.
Okay, sir. Okay.
Then we can observe actually.
This is definite energy state. Look at here. Write down. That term came, isn't it? That word came. No, that's what I have said, Amar. They are states of definite energy. Definite energy state.
If this width is smaller and smaller, we can observe.
Width is 0. Definite energy.
Yes.
Okay? Before toss only you know that.
Sir, here width is 0 can we relate that there is no spirit in the position also?
Oh, no. You are not doing position measurement. You are doing energy measurement. Again, in this state, there exists sigma x greater than 0, sigma px greater than 0, multiplication greater than or equal to h bar by 2. That is followed. But sigma h, that can be 0. Okay? So, look at here. What can happen in quantum mechanics? I mean, what are allowed in quantum mechanics? You can't have very well-defined position state. You can't have very well-defined momentum state. You can have state in such a way that these two multiplication is always greater than h bar by 2. Okay? Greater than or equal to. But you can have a state with sigma h equal to 0. Is it okay? We call that one as definite energy state. Is that okay? No uncertainty. That's why you are what is the measurement you are doing? You are doing energy measurement. What is the value you get? You get E. That's why that separation constant is called as energy of the system. Is that okay? Quickly, next one again. Now look at here. What will happen in this case while solving this one? You will get different energy E1, E2, E3 like that, corresponding different wave function. Let me write like this. Okay, you will get one wave function psi1 of x corresponds to energy E1. Okay, you will get another wave function psi2 of x corresponds to energy E2. You will see that one later and so on. When you solve this differential equation, you will end up with this one. That means h cap into psi1 is equal to E1 into psi1. Okay, h cap into psi2 is equal to E2 into psi2 and so on. Okay, while when you solve this one, there are some restrictions that will come in particle in the box, harmonic oscillator, even in hydrogen atom. Okay, so that you will get different solution. Okay, different solution. Correspondingly, you will get energy. You will see that one. Once we solve, you will get to that. Now look at it. Corresponds to this one. I call this one as psi1 of x comma t. That's equal to psi1 of x into e power minus I e1 t by h bar. Okay. Corresponds to this one. I call it as psi2 of x comma t. E power minus I e2 t by h bar and so on. You will end up with this situation when you solve time independent Schrodinger equation. Now look at here, this is also solution. These are all solution of time dependent Schrodinger equation, isn't it? Time dependent Schrodinger equation, earlier equation. Now linear combination is also the solution. Linear combination is also possible state. This is non-classical idea. Because it's a linear differential equation. I will come to that point in the differential equation part. That's a linear differential equation. That's a property of linear differential equation. If you have different solutions, linearly combine them, that's also solution. Linear combination is like this. So we call this as most general solution. That's equal to C1 into psi1 of x comma t plus C2 into, these are all stationary states. These are all individually stationary state. Once you see this one, you should say it is stationary state. Is that okay? So C2 into psi2 of x comma t plus C3 into psi3 of x comma t plus and so on. Can I write in summation? That's the best idea. Summation over Cn into psi n of x comma t, n is equal to 1 to infinity. This is the most general solution. Look at here. If you put C2, C3, C4 and all 0, only C1 non-zero, that will be stationary state again. That's why this is the most general. That's what I'm saying. Suppose if you make C1 0, C3 0, C4 0, make C2 non-zero, then that will be second excited state, psi2 state, like that. Is that okay? Energy with energy E2. This is called as most general solution. Or you can write like this. The best way to write n is equal to 1 to infinity Cn into psi n of x into e power minus I en t by h bar. Now look at here. Once, if any two of these are non-zero, this is non-stationary state. This is non-separable also. Just check that out. So psi1 into e power minus I e1 t by h bar, okay, C1 plus C2 psi2 e power minus I e2 t by h bar. Can you separate variable now? Separate the time part which is multiplied with space part, you can't do. Once you add any two of these, that is non-separable solution. That's why again whatever separable solution we have chosen, again in the first part, that's not that bad. It gave non-separable solution also. You will understand. I'll give some more idea, okay, later. Is it clear? And one more thing is, any solution of Schrodinger equation is a possible state. You take like that. It's a theorem.
What's that?
Any solution of time dependent Schrodinger equation is a possible solution, possible state.
Now, repeat
Again,
again.
this equation is there. Am I right? I h bar dou by dou t is equal to h cap into psi. Am I right? Any solution, whatever solution you take, that is a possible state of the particle. This is also solution. This is also solution. Linear combination is also solution. That's why linear combination is also possible state of a particle. That's what I'm trying to show. Is that okay? Particle can be in the ground state with energy E1. Particle can be in the excited state with energy E2. Particle can be in the linear combination state. It's a property of that equation. Look at here.
Yes.
It's a property of linear differential equation. I mean, we found that equation in that perspective only, am I right? It should allow superposition. We call this in a superposition state also. This state. This is the most general. This is one of the examples. C3, C4 and all are 0, only C1, C2 not 0. Okay? We call this one superposition state also. Or linear combination state, that's the more better word. This process is called linearly combining them. You are not taking square and square cube and then combining, am I right? You are just multiplying with one and first power of that one and you are combining, linearly combining them, okay?
So here wave function is not normalized.
Wait a second, to normalize this, this linearly combined state, to normalize that one, we need to go for other probabilistic interpretation. That's a good question. You can definitely normalize it like this, okay? Psi general solution x comma t, psi general solution x comma t dx is equal to 1. You can enforce this condition, okay? Later you will find this condition is equivalent to mod Cn square summation over n should be equal to 1. You have the Cn. This condition will be equivalent to this condition. Let me prove this one. It is there here. Let me prove in the next class, okay? Over. Now I'll give some MCQ, but you may not able to solve some measurement problem, but most of the problem you can deal with it, okay? So that's why I was pushing you towards this chapter. Now I'll do one more interpretation, then I'll close this session, okay? We better not to have next session, okay? If possible, I'll have one session in the evening. Evening I'll take only after 6:30. You don't have to worry. Suppose if you have any class, okay?
The summation of Cn square will be 1 means all the.
What I'm saying is, this is a way of normalizing this one. Am I right?
No,
this
Cn square mod means C1 square plus C2 square.
Mod C1 square plus mod C2 square plus mod C3 square and so on. That summation should be equal to 1.
But earlier we are saying that a constant, a e to the power.
That is suppose if you have this one, psi stationary state, am I right? X comma t is equal to psi of x into e power minus I e t by h bar. If you want to normalize this one, you go for that method, okay? But if you want to normalize this one, usually, so again, this is equivalent to this one. I'll show that one. You have Cn into psi n here, isn't it? This way of writing this one is equal to 1, okay? This process, okay, is equivalent to this process. That's what I'm saying, equivalent. We can show that one, okay? We can show. And there is one more probabilistic interpretation here. That's what I'll do now, okay? Now, if you have a solution like this, general solution, okay? Or wait a second, I'll come to that point little later, little moment, okay? Yeah. And we shall finish this out so that you can solve some problems, okay? Otherwise, if I upload problem, you can't solve all, okay? What will happen is, so they will provide you x comma 0 initial state. That initial state need, again, when you put t equal to 0, look at here, when you put t equal to 0 in psi 1 of x comma t, psi 1 into e power minus I e t like that, am I right? If you put t equal to 0, what you get? Psi 1 of x comma 0, what is this one? Psi 1, am I right? Psi 2 of x comma 0, what is this one? Psi 2, isn't it? You will get like that. But they will provide you the state which is none of these. Something else. They say this is the initial state. And they will ask you to find what is the state at later time, t.
Something else means? Something else means?
Something else means some other function. Suppose if you take particle in a box, okay? So your stationary states means root of 2 by a sine n pi x by a. Okay? But they say initial wave function is like a into x into a minus x. Some parabola. First problem in a particle in a box. This is none of this. This is none of this. But we shall see later, lot of theorem, okay? Mathematical proof. This can be written as summation over Cn into psi n of x. They will give initial state like some other function which is none of these stationary states. Okay? Some other function. But mathematically, we have a lot of theorem and all. We can write that given state, whatever state it is, in terms of this one. So in case of particle in a box, our Fourier analysis gives a backup why we can do like that. So gives a proof how we can do any function in terms of this one. Isn't it? How? Yeah, I said any function can be state actually. Any normalizable function can be state actually. Quite more general. Wait a second. Again, after next part, after particle in a box, it will be very clear for you. Okay. Particle in a box we need to study for a little long time. Then you will understand that. Okay. Is that okay? Now again, look at here. Whatever state you have given, this is a kind of theorem. Okay, we call this one as a completeness theorem. Whatever these psi 1, psi 2, psi 3, this is a kind of linear algebra concept. We will understand later. Okay, hold on. So again, whatever state you can write in terms of linear combination of them. Just like in case of 2 dimension, suppose I cap and j cap are unit vector, arrow vector space. Okay. So any vector A can be written in terms of I cap and j cap. Ax here, Ay here, isn't it? Ax here, Ay here. Like that, again here you have infinitely many. Here you have only 2, I cap and j cap. 2 dimension. Here we call this as infinite dimension. I'll come to that point. That's why we don't go for Heisenberg approach in the beginning. Because matrix mechanics could be quite lengthy. Okay. So that's why we deal with Schrodinger approach. Later we go for matrix approach. When we have only 2 possible state, spin state. When we have only 3 possible state, angular momentum state, L is equal to 1. Then we go for matrix approach. Okay. So it is very similar to that one. Any general vector, any vector in a plane, am I right? Any vector in a plane can be written in terms of I cap and j cap. Very similar to that one. Any function can be written in terms, any normalizable function, okay, can be written in terms of linear combination of this one. Or in other words, any state, any generalized state can be written in terms of eigenstate. Can I say like this? Any generalized vector can be written in terms of unit vector I cap and j cap. Any generalized state can be written in terms of linear combination of energy eigenstate. Is that okay? So then the next idea is to find this one. You just look into your earlier equation, whatever I have. What is this one? N is equal to 1 to infinity. This looks like our generalized solution. That's it. This is our generalized solution. Cn psi n of x into, you just plug in e power minus I en t by h bar. So from initial state you got to some state at later time. Process, I am just talking about a process. Okay, you do some problem, you will understand. Process. Suppose if your psi of x comma 0 is suppose psi 2. It need not be psi 2, psi 3 like that. Okay, it can be any general function. If it is a general function, write that one in terms of this one. It is possible in principle. I'll show you that one. Okay, if it is psi 2 itself, psi of x comma t, you just write psi 2 of x into e power minus I e2 by h bar, e2 t by h bar. If it is some general function, write it as a linear combination. It can be written. We have some theorem over there. Okay, mathematical theorem. So again, once you write like this, again your later time, this one, isn't it?
Okay.
Is that okay? If initial state is one of the eigenstate, later time just plugging this one. Suppose if your initial state is C1 psi 1 plus C2 psi 2. So what is this your later state? C1 psi 1 e power minus I e1 t by h bar plus C2 psi 2 e power minus I e2 t by h bar. If initial state is some general function, try to decompose that one in this manner. I'll tell you what is the mathematics behind that one.
So here the time is not changed. After some evolution, time T1, T2 will not.
No. After one time, I'm talking about one time.
No, if I will take 1 second, after 1 second.
Oh, if you put t equal to 1 second, here also you should put t equal to 1 second, here also t equal to 1 second. These two are not different. T is same.
Yes.
Everywhere t is same. Everywhere x is also same. Psi1 of x, psi2 of x only. Okay?
Sir,
Yes. We call this one as superposition of states. Okay? We call this one also superposition of many states. Yes, tell me.
sir, in vector like unit vector, in web function psi1, psi2 are we can call unit vector.
Similar. They will play the similar role as unit vector. I'll show you that one. Okay? I think in particle in the box I can make it more better way. Okay? But here I need you to know these things to solve some problems. Okay? That's why I'm just proposing these things. Okay? Now, last concept. Again, I'm going to do all of this again in a particle in a box problem. Last concept. Yeah, you have written this one. Am I right? General solution. Any state that's equal to summation over Cn into psi n of x into e power minus I En t by h bar. Isn't it? En is equal to 1 to infinity. You said this is a general solution, superposition of states, superposition of 3 state, 2 state, anything can happen here, isn't it? Anything can be the possible state, isn't it? Because that's also possible solution of Schrodinger equation. All possible possible solution of Schrodinger equation is a possible state of the particle, okay? Now, the question comes, if you do energy measurement.
Sir, one question is there. What happens if we done energy measurement in the storage?
That's what I was trying, okay? If you do energy measurement here, whether you get E1, E2, E3, what you get? Isn't it? No, this is not definite energy state,
Yes.
okay?
Yes.
This one was definite energy state, Psi2 was definite energy. This is not definite energy state. It is a superposition of different energy states. Superposition of states, look at here, it came here.
Oh, we can say like.
Exactly same as superposition of 2 translational states. Here it is superposition of 2 energy states. Not only 2 energy states, it can be superposition of 3 energy states, 4 energy states. You make more number of slit. That is double slit. You have only 2 translation state. Am I right? You make 3 slit. There will be 3 translation state in case of double slit.
So we will get.
This is superposition of different energy state. Can I say like this? Superposition of different stationary state. So superposition of different energy state, definite energy state. Superposition of different definite energy state. So can I say like this? Once it is a superposition, that definite become indefinite. Isn't it? Indeterministic. Isn't it? Without measurement, you can't say whether you get E1, E2, E3 or something.
Okay, then sir, it will come like either E1 or E2 or E3.
Before measurement, you can't say anything. But you can say anything about something about probability. That's what I told.
Yes.
We define probability here. C2, Psi2, e power minus I E2, t by h bar, and so on. Is that okay? Now, if you do measurement, whether you get E1, E2, okay, the question here is, what is the probability that you, again, if you do energy measurement, what is the outcome? Outcome is, look at here, either E1 or E2 or E3. Not like E1 plus E2 by 2. E1 plus E2 plus E3 by 3. Not a kind of average. Not like electron pass through both slits. That's what you don't observe, isn't it? If you do observation in case of electron double slit experiment, so if state is when you are not observing, it is in psi1 plus psi2 state, isn't it? When you observe, you will get either psi1 or psi2. Similarly, okay, if you do observation, either you will get this state with energy E1, or you get this state with energy E2, or if you do energy measurement, either you will get E1 or you will get E2 or you will get E3. Indeterministic now, isn't it? You can't say anything. Before the measurement, you can't say that this is going to happen here, isn't it? just like in case of electron double slit. Try to compare this one with electron double slit. But you can say probability. If you can't say which energy that you are going to get, okay? Remember, your energy measurement outcome should be either E1 or E2 or E3 or E4. Suppose if you throw a dice, you should get either 1, 2, 3, 4, 5, 6. Will you get 1 and 2 combiningly? No, isn't it? You don't get like that here. You don't get the energy E1 plus E2 by 2. You do energy measurement outcome. If you do measurement outcome will never be any intermediate value. This is either E1 or E2 or E3. Just like tossing the coin, you will get either head or tail. Isn't it?
Before measurement.
After measurement, I'm saying. After measurement, you will get either E1 or E2 or E3. Before measurement, you can't say anything.
Okay.
Before measurement, you can't say anything. Exactly the same situation came here. That was stationary state. Before measurement only you can say. Stationary state idea is different. Okay, this only if I write psi1 of x into e power minus I e1 t by h bar. This is stationary state. Definite energy state. Before measurement you say its energy is E1. System has energy E1. Here you can't say before measurement. You can only talk about after measurement here. Here after measurement you get E1 only, whatever the measurement you do, isn't it? Here you say after measurement you get either E1 or E2 or E3, just like tossing the coin. What is the result? Either head or tail, am I right? You don't get result head plus tail divided by 2. Meaningless, isn't it?
Definite and indefinite.
This is definite energy, this is indefinite energy state. You can say like that. You will get some standard deviation in the measurement of energy. You work out problem. Now look at here. Now the question, possible energy measurement outcome, there is either E1 or E2 or E3. Possible measurement outcome in case of double slit experiment. Either it will pass through slit 1 or it will show off as it's passed through slit 2. Possible outcome in case of head and tail, either head or tail. Possible outcome in case of dice, number 1, number 2, number 3, number 4, number 5, number 6. Isn't it? Like that here. You don't get any E1 plus E2 by 2 or average of all of this E like that. You don't get that. Indeterministic come here. But if you can't say whether I get E1 or I get E2 or I get E3, you can at least say what is the probability of them, isn't it? That probability of getting E1, that's equal to mod C1 square. Probability of getting E2, that's equal to mod C2 square. And so on. Or in general, probability of getting En in this kind of state, that's equal to mod Cn square. Another probabilistic interpretation. Later we shall show this is equivalent to our earlier position probabilistic interpretation. Here you can't see. But this is discrete probability interpretation. This is discrete probability. P of E1, P of E2, P of E3. Energies are discrete. I have taken energies are discrete, not continuous variable. Position probability, position was continuous variable. That's why you had continuous probability density concept. Am I right? Probability density concept. This is a discrete variable. We did two problems, am I right, in probability. One is discrete variable, other reason is continuous variable. This comes in the continuous variable part. Hold on a second, okay, I'll continue. Once this is probability, total probability should be equal to 1. Then summation over mod Cn square, n is equal to 1 to infinity, this should be equal to 1. This is the normalization condition in this case. If these are individually normalized, okay? When you linearly combine, the total wave function after combination need not be normalized state, isn't it? So we should enforce this condition if it is not normalized. And you will see that this is equivalent to doing it like this. This is GS, okay? These two are equivalent actually. These are individually normalized, but once you linearly combine, it need not be normalized, isn't it? You enforce this condition. But that condition is same as this condition. This should be obvious condition. Why? once you define this one as probability, total probability should be equal to 1. Isn't it? That's why we call this as normalization condition. But these two are mathematically equivalent. Let me show that one later. Okay. This is the probabilistic interpretation. If possible energy measurement outcomes are either E1 or E2 or E3 and so on. Possibility.
Hello,
You can't say, yeah, yes, tell me. Yeah.
Yes, sir. While calculating psi GS star, psi GS, we are having some term like C1, C2.
Yeah, you will get C1 star, Psi1 star like that. You will get very lengthy term here. But we can show that this is equivalent to this one. This will turns out to be like this. These are normalized.
We are also having term like C1, C2, Psi1, Psi2 to the power minus.
That integral will be 0. We have one more property there.
Oh, yes, sir.
No. When you multiply these two, you will get Psi1, Psi2 term, isn't it? C1 star, C2 like that. Those integral will be 0. We call that one as orthogonality relation. That comes as a later concept. That's why I am not going to prove this one. That's why he didn't prove this one. He proved in a particle in a box. Okay? We shall prove it later in the particle in the box. Okay? We explored some other relation to show that this is equal. Yeah, that's a good question. If psi1 square, psi2 square, everything is there, that integral equal to 1. That is normalization. You know that one. But still you don't know that orthogonality. One more relation. This relation, integral psi1 star into psi2 dx. This is equal to 0. You will understand this one in the next topic. Okay? So that's why all cross term will vanish when you multiply this one with this one again, isn't it? That's what you are thinking. All cross term will vanish. That's somehow it will come. But both are equivalent. Sometimes you need to go for this one. Sometimes you need to go for this way of normalization. I'll tell you when. Okay? Yeah.
In linear combination state, we can try that one or this one.
Or this one. Sometimes this is easy. Sometimes this is easy. Suppose if linear combination state contain only 2 to 3 term, this is better.
Yes.
Add mod square equal to 1, you get. Suppose that initial state is some generalized function.
Yes.
If you expand that one in terms of this one, if suppose it contains infinitely many terms, just like your Fourier analysis.
Like sin x.
No, not sin x. I mean, I don't take any example here right now, okay? Suppose if this contains infinitely many terms, then this will be very tedious task. Then we go for this one. You will understand after solving problem, okay? But just remember these two are equivalent, minus infinity plus. Yeah, now question, quickly.
Sir, here e to the power minus I e n t by h plus is constant term.
Not constant, it is variable with respect to time, but it's complex actually. You can't draw that easily. You can't draw it.
That's why we get probability.
But it is independent of x actually.
Sir, like we draw exponential term, we cannot draw this.
No, I is there. Cos theta plus I sin theta. How do you draw? You should go for complex
It
planes.
saves us.
Huh?
I saves us.
I saves us. Why?
Because when I take a star,
Huh.
star that
Star it will go, isn't it? No, it will not go everywhere. In this state, it will not go. If you take mod psi square, it will be time dependent in this state. You just check that out. There is a problem. Example number 2.1. Yes.
So we can say like that if we are finding the time evolution of an initial state, then it should be expanded as a linear combination of the
Energy eigenstate. I'll come out with the theorems like that. Okay. It should be expanded as linear combination of energy eigenstate. Then later function can be written as plugging in this factor. Okay. Now you should read the second chapter today. Look at here. Note this down. Have a note on this one. Okay. You write this expectation p cap square. Am I right? That's equal to psi star minus h bar square dou square by dou x square into psi dx. Am I right? You write like this. There is a idea in case of again Hermitian operator and all. Okay. One of this dou by dou x can be taken here. This can be written as this minus h bar. One more negative sign will come plus h bar square integral dou psi by dou x the mod square. Expectation p cap square positive, you have negative here. Okay, you have negative here. Or expectation p cap square by 2m, if your expectation t. I'll tell you in the next chapter, or the third chapter, okay? Again, because dou by dou x, it's an anti-Hermitian operator. If you take it here, one of the dou by dou x, it will become negative. So that dou psi star by dou x, dou psi by dou x, you can write it like this. Complex conjugate to each other, okay? This is a way of, because you can avoid second derivative. You can do first derivative, you can take square, isn't it, in this step. So this is equal to plus h bar square by 2m into pi 2m would come, that's it. Expectation minus infinity to plus infinity mod of dou psi by dou x whole square dx, okay? This is mathematically proved. This is not restricted to any one particular problem, okay? Mathematical proof is there. This is expectation t. This is expectation p cap square. Use these things. Quite easy. So you have to use this one in some problem, okay? You will understand later. Some problem you have to do this one. In some problem, what will happen is first derivative will be discontinuous. Second derivative will not exist at all. Then you should take only first derivative and you should take mod square and you should do that one. Sometimes wave function will be continuous, but first derivative will happen to be discontinuous. You can't go for second derivative. Even if you go for second derivative, that will be very mathematically so tedious step. Then you just take first derivative, you just do that one. Is that okay?